and Galaxies cosmological simulation. Yeah.
All right, thank you, Andrea. And thank you, Rosdahl, and the other organizers for having me here. So I'm going to attempt in an hour and a half to teach you how to run and analyze cosmological simulations. So let's get started. So first of all, why simulations? So galaxy formation is a gigantic loop on cosmological scales after the Big Bang. Dark matter collapses into this cosmological web of sheets and filaments and halos. Baryons, the gas, they fall into the gravitational potentials of the dark matter. Because the baryons can cool radiatively, they form relatively compact structures, galaxies, inside those halos, inside which the gas continues to collapse onto smaller and smaller scales into these filaments, molecular clouds, and eventually form stars. These stars then inject energy into their surroundings in the form of radiation, supernovae, stellar winds, which cascade back to larger and larger scales, eventually creating galactic winds and radiation, which escapes from those galaxies and affects the gas, which is trying to fall into the galaxy. So this creates a gigantic feedback loop over a huge range of scales. It's a nonlinear, multi-physics, multi-dimensional problem. We have no laboratories to make galaxy evolution experiments. And simulations are really the only way to gain an understanding of galaxy formation. So just a bit of overview of the presentation I'm going to do. I'm going to start with a little bit of the history of cosmological simulations. And then I'm going to give you a crash course in how to do them. I'm going to talk about subgrid recipes and what happens then when we try to have higher resolution and more physics in our simulations. And then we'll talk about reionization, the first stars, and high redshift galaxy simulations. Okay, so to first order, you can run very simple galaxy evolution simulations by just considering gravity. To first order, galaxy evolution is completely dominated by gravity. And if you want to do that, you can run n-body experiments where each particle represents a dark matter or stars. And you can evolve these equations, which just describe the evolution of your movement according to the velocity of each particle, and the acceleration of each particle according to gravitational forces. And the gravitational force is just sum of the gravitational force of every other particle in your volume. And then you can discretize this, so you can change the infinitesimal dt into a finite dt, which is just small enough that it doesn't affect your results. And then you can evolve with a scheme such as the leapfrog scheme, where you evolve first the positions over half a time step, and then you cross over with the velocity over a full time step, and etc. They jump over each other. This is very easy conceptually, but it takes a very long time because there are n squared operations to solve this. For every particle, you need the force from every other particle. Now, this is also how people first simulated galaxies. Can you actually guess when the first galaxy simulation was done with methods like these? Can anyone guess roughly the time? I think the first computer was invented like in 1944 or 1945, towards the end of the Second World War. 60s? It's a good guess. This was in 1941, I think. So it was actually not done with computers. So this is I think it's kind of acknowledged that this is the first galaxy evolution experiments. This was done by Erich Holmberg in 1941, and it was done with light bulbs, not with computers. So they set up 74 light bulbs, and they had some kind of a sensor which could, on each light bulb, which could measure the light. And this actually can kind of replace gravity because the light dilutes as radius squared. And then they just meticulously moved each light bulb according to a tiny time step, and they did this for a very long time. And they could run this simulation of two galaxies merging. And they found that this forms a kind of filaments and kind of cluster formation in those galaxies which are merging. Okay. Then people started using computers, indeed in the 60s, so very good guess. First, it was pure n-body, and it was non-cosmological, so it was more galaxies like these mergers, just with more and more particles. I can go to the next one. And then in the 70s and 80s, people started to do cosmological simulations, again with more and more particles. I don't think we had the anisotropies, isotropies, yeah, thank you, from the cosmic microwave background yet, but people could kind of predict what they would look like before they were observed. So people were doing cosmological simulations and actually starting to establish a cold dark matter model. I should not go without mentioning the Navarro, Frank, and White halo profile, which they used the simulations to develop. And they also had to, they had to use these inventive schemes to make visual representations in that time. They couldn't use color tables, so they had to use ASCII to represent the densities of dark matter in their simulations. There's a bit of delay in switching between slides. Here it is. So in the 80s and 90s, there start to be measurements of anisotropies from the CMB, and also people start to do simulations with gas, with baryons, so hydrodynamic, so N-body plus hydrodynamic simulations. And quickly, people start to realize that there is this overcooling problem, that if you just let baryons fall into the gravitational potentials of the dark matter halos and form stars according to simple recipes, they form stars way too quickly compared to what you observe. Then there is this landmark Millennium simulation, which was already mentioned on Monday, where using pure N-body simulations of dark matter with many, many particles, 10 billion dark matter particles, they could kind of reproduce the observations of the local universe around us, so the cosmic web. And then in the 2010s, there was this, it was kind of the era of cosmological hydrodynamical simulations. So there were many, many cosmological simulations projects that you can see kind of listed here, which had, large volumes, typically something like 100 co-moving megaparsec wide. So resolving, thousands, even tens of thousands of galaxies, but not really the interstellar medium in those galaxies. So resolution typically of kiloparsecs in spatial resolution, and 10 to the few solar mass dark matter and stellar population particles. So during that time, there were a lot of efforts to develop subgrid models to overcome this overcooling problem. And then using calibrations to reproduce a large range of observations, such as the star formation rate density, stellar mass function, etc. So calibration, that was, in the beginning, that was a thing that people would not really admit to doing, but really, people were calibrating, they were adjusting their subgrid models to reproduce these physical properties or observed properties of galaxies. So calibrating basically supernova feedback to suppress star formation at low galaxy masses and to suppress star formation at high galaxy masses with AGN. So, it was necessary because these simulations, they could not resolve the interstellar medium of their simulated galaxies. And it helps to gain an understanding. You see what you need to do to kind of reproduce galaxies. You see that you need strong feedback, for example. But at the same time, it can be a bit not helpful in the sense that you can get to the same solution in very, 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 very different ways. For example, you can suppress star formation in galaxies by ejecting all the gas from the galaxy. Or you can allow the gas to accrete onto the galaxy, but just prevent it from forming stars once it is inside the galaxy. So just to show the evolution a bit of cosmological simulations over the years. So it basically follows the famous Moore's law of exponential increase in computational power over time. But this is also helped by developments in models for example, solid gravity, like I was showing you before, and in better parallel methods for basically splitting between many CPUs when performing a simulation. not really where are we now, but more where were we 10 years ago. So there was kind of the impression by all these simulation projects like Eagle and Fire and Nihao that the problem of galaxy evolution was kind of solved. We could reproduce most observational properties of galaxies at redshift 0. But I mean, it was calibrated. This solution could be reproduced in many different ways with many very different subgrid models. And there were also strong hints of disagreements with observations at a high redshift, so even before the advent of the JWST. And at the same time, people were starting to experiment with much higher resolution simulations, resolving individual galaxies in each simulation. And when you did that and injected less and less calibration on the physics, you were attempting to do first principle physics in your simulations. It actually became tougher and tougher to reproduce this observed suppression in star formation. So now I'm going to give you a quick crash course in how to run cosmological simulations. If I can get to the next slide. So I've already shown you gravity. That's really the first order, to first order what dominates galaxy evolution, but you also need to include gas and star formation in your simulation. So you need to solve the Euler equations, which describe the conservation of mass, momentum, and energy. And then you close this with an equation of states, which relates energy, the internal energy of the gas, to its pressure. And note here, this includes the gravitational potential from all the gas, all the stars, and all the dark matter in your simulations. And this is usually solved not in the simple way that I was showing you before, which is O to the number of particles squared, but you use methods to make this quicker. For example, with grids, you kind of paint the gravitational potential to the grid in your simulation. Or if you're running particle simulations, you kind of collect groups of particles into one kind of blob and compute the gravitational potential over large lengths according to those individual blobs. There are, like I hinted at already, there are two kind of classes of approaches to how you solve these Euler equations. So one is Lagrangian, where you split your volume into particles which move around your volume. And Eulerian, where you just split the volume into grid cells, where the fluid moves along the interfaces of the grid cells. And you can also combine these methods by kind of constructing a mesh, a kind of mesh which can have different forms around those particles, a mesh which then moves along with the particles, like which is done in the repo code. Yeah. This, I mean, I'm showing you a very, very simplified version of how this works, and but of course this is a lot more complicated if you go into the details. But we don't really have time to do that. There are several codes on the market to perform cosmological simulations, and as you can see here, almost all of them are public. So you can go online, you can download a code, and you can start running your cosmological simulations. They vary, however, in how much physics is included in the public version. So in some versions, you really just have the gravity and the hydrodynamics, and there are no methods for forming stars, for example, for the cooling, etc. But other codes, they do have most of that stuff, and you can actually start running pretty sophisticated cosmological simulations from the go. I'm just showing here kind of advertising because Ramses is the code that we use, and most people in France actually use the Ramses code, mostly because it was written in France. It has recently become kind of a publicly acknowledged code. It's like an observational service in France, so people can actually be hired on kind of a Ramses support. And as a result of that, there is a lot of kind of structure around the Ramses code. You can download a pretty sophisticated version of the code and also a tutorial for using the code for all kinds of different simulations. For example, galaxy merger simulations and cosmological simulations. So I recommend if you're kind of interested that you go to the Ramses website and you just try it out. You can try it out on your laptop. just to give you an idea how you discretize your equations of hydrodynamics on a grid in this case. I'm just going to show you how it's done on a grid. So you start with an equation here for the conservation of momentum. So it has infinitesimal time at delta t and at delta rho. And you just make that a finite one. So the delta x really becomes of your cell. And the delta t is really just subject to the current condition. Does anyone know what the current condition says? It just says the time step should be small enough that you cannot cross more than one cell width in one time step. So that translates as the width of your cell divided by whatever fastest speed is in your simulation. So sum of the sound speed and the gas velocity, for example. And then you just do some algebra on this equation, and then you can solve for the flux of gas between neighboring cells. You do that once over this interface, and then for this interface, and then for the interfaces in the other directions. And then you're basically done. You just need to do that for every cell in your simulation. And then you repeat for delta t until you have reached a Hubble time. So you need, in principle, to do many, many delta t's. Typically, in a cosmological simulation, delta t is a few tens of thousands of years, even hundreds of thousands of years. Okay. So there are other components. If you run a cosmological simulation on a grid, if you use a homogeneous grid and your box is 100 megaparsecs across, you're not going to get close to resolving galaxies. So you need to somehow focus your resolution on galaxies. In SPH codes, this comes naturally because, well, you start with a kind of homogeneous distribution, but the particles, the gas particles, the dark matter particles as well, they fall into these dark matter potentials. So they kind of automatically focus your resolution on the galaxies. In AMR, so in grid codes, sorry, this does not happen automatically, but you can use adaptive mesh refinement, which is what I think all the mesh codes use, where you kind of split your cells into children cells, which can then split into children cells recursively, usually according to mass. So then again, you kind of focus your resolution on where the densities are high in the interstellar medium and the surroundings of galaxies. The nice advantage of AMR is actually that you can also focus your resolution on something other than mass. So you can actually start resolving, if you're interested in resolving cosmological voids, you can choose to do so with AMR simulations, and that you could not do with SPH. Then simulations, they have to be parallel. If you want to run, again, cosmological box, 100 megaparsec in width, you cannot do that on your laptop realistically unless you have very, very low resolution. So the way to get around that is to split your volume and hand out each subvolume to different CPUs. And then each CPU just churns on its volume, and then they just have to communicate fluxes of gas, of particles, across the interfaces between the different CPUs. And in that way, you can potentially, if you have 10 CPUs, your simulation becomes 10 times faster than if it were to run on one CPU. There is a limit to this, though, because eventually, if you create too many subvolumes, then your computation starts to be dominated by the communication between cells. So usually, the code scales well up to a certain number of CPUs, and then the speed starts to, you stop to have a gain in your speed when you increase the number of CPUs because the computation becomes dominated by communications. So then there is the cosmology. If you want to use cosmological simulations, you have to start with initial conditions, which are based on the cosmic microwave background, so Gaussian fluctuations in the density distribution of dark matter. I've been asked, actually, where is in a simulation like this, where is the Milky Way? Can anyone guess where the Milky Way is in this particular simulation? It's a bit hard to see because it's not very, the resolution is not very high. Would anyone guess? At the center, maybe? At the center? Yeah, it's a good guess. I would put it at the center as well. But there is no Milky Way, of course, in a simulation like this. This is not our universe. It's It's a universe which is statistically equivalent to our universe in the sense that it has the same distribution of density fluctuations in the initial conditions. Then you use periodic boundary conditions. So also a cosmological simulation is almost always much, much smaller than the observable universe. So in this particular case, the box width is 20 co-moving megaparsec. So you just use periodic boundary conditions. If you go out on one side, you basically come in on the other side. And then to express the expansion, yeah. Indeed, sorry, just before you start, I forgot to say in the beginning, I completely, it's very nice if you ask questions, actually, so I encourage that.
How do the boundary conditions affect the time simulation?
So I think if your box is kind of not big enough, then it starts to affect your simulation. But if I don't even really know what the kind of minimum size is like that, but I think if you have a very small box, then you are affected. And there were, in the beginning, I remember there was some issues, but they were numerical issues with boundaries. And I think once those are fixed, it's not really a problem. So to express the expansion of the universe, you don't expand your box, really. You just change the definition of the size of the cell according to your cosmological model, according to the time of the simulation. And then there are zoom simulations. So if you run a full cosmological box with the same refinement scheme everywhere, you typically resolve tens of thousands of galaxies, but at the sacrifice that each galaxy is not very well resolved, or at least you need a lot of computational resources to do that. So the way around that, if you want to really focus your resolution on an individual galaxy or its environment, then you can use cosmological zoom simulations. So this is a very common approach that you read about in many papers about simulations. Then you take just the same cosmological box as I was running before, actually. But you allow the resolution to be low in most of the box, and then you kind of define a region which you identify by running a pure dark matter simulation of the same box. Pure dark matter simulations are very cheap compared to having the gas as well. So you can easily do that, and then you can identify the halo that you're interested in the full cosmological pure dark matter simulation. And then you can rerun where you focus your resolution. You only allow adaptive refinement, or you have just, if you're running an SPH simulation, you kind of have much more particles around that targeted halo. And then you can focus your resolution on this individual halo, but everything far away is very, very coarsely resolved. You have it there for the kind of large-scale gravitational effects, but you're not doing any analysis of anything which is outside this zoom region in your simulation. And then you can afford to have a very high resolution in your galaxy, and you can start to resolve the ISM and the feedback and the star formation which is going on in that galaxy. But at the cost of statistics, instead of tens of thousands of galaxies, you have one. And to add to that, actually as well, there is also the problem of scaling when you're running zoom simulations. Because like I was saying, you can, if you run a cosmological simulation, you can split your volume into subvolumes. If you're running a zoom simulation, you want to split a tiny fraction of the whole volume into subvolumes. And then it actually becomes much, much harder to scale to many, many CPUs. So you can only afford to go to a smaller number of CPUs before your kind of improvement in computation starts to go away. So now the question is, how do these different methods and different codes compare when they are running the same initial conditions in cosmological simulations? There's a nice project called Agora, which have now many, many papers comparing different codes in different aspects. In the first paper, they show just pure gravity simulations, how they compare, and they compare quite well. I mean, there are tiny, tiny differences in the distributions of halos, but they pretty much get the same halo mass function and more or less the same distribution. If you add gas to those simulations, you start to see differences between the different codes, and the largest differences are actually between AMR, which are here, and SPH, which are here. So that's due to mostly how volumes are refined differently between the SPH and the AMR methods. However, these differences, which are there, they are completely dwarfed by the differences that eventually come when you start to add subgrid models for star formation, for feedback, and for cooling in your simulations. So here's a comparison of now a galaxy which is formed using methods for cooling, for star formation, and for feedback. And not the same methods, just using everyone's favorite subgrid methods in whatever code people are using, or from whatever cosmological simulation project they are using. And you can already see that the morphology of the galaxy, which started from the same initial conditions, is quite different with different codes. So in some cases, you even get elliptical diffuse galaxies. In some cases, you get quite disky galaxies. And this is not due to the SPH versus AMR or something like that. This is just due to the different approaches that these groups take to using their subgrid physics.
So, like the morphology is different, but is like the synthesized spectra and like other kinds of like derived parameters, like do they differ as much?
Yeah, sure. Absolutely, because also if you look at, for example, the star formation histories of those galaxies, they are going to be quite different. Some galaxies which will have formed their stars relatively early, others relatively late, etc. Yeah.
These are gas maps, right?
These are kind of mock observations. Yeah.
But if you compare only the black matter structure, they have more serious difference just for some.
Pretty much exactly the same. Yeah.
Okay.
Yeah. So the dark matter, like there are many works that have looked at how the baryonic physics are going to affect the dark matter halo formation, and there are very little and very subtle effects on the large scale. On the very, very small scales, you can get cuspy versus chord halos and stuff like that, but on large scales, none at all.
Sorry, I can also ask the question. What strikes me is not as much different shape, but the sizes are very different.
Yeah.
So that means that angular momentum as well is
Yeah.
some problem.
Well, I mean, so I think in some of these simulations, let's see, probably this one, you literally.
And are, I mean, they're very small. Sorry.
I think these are differences in the feedback, probably, mostly to some degree in the star formation as well. So in some of these recipes, you literally take gas and you kind of decouple it from the galaxy. You transport it to the circumgalactic medium, and there you let it go away, right? So you're basically transporting the angular momentum out of the galaxy, right? And for sure, this is going to affect the sizes of the galaxies. There is also a chaotic effect, which I think we can discuss later. But if you simulate an individual galaxy, there are very small scale effects which can actually affect how the galaxy evolves over the next 100 million years, say. Yeah. So you can actually run the exact same simulation, a cosmological zoom simulation, with slightly different variations in the random numbers that you're generating for star formation, for example. And this is going to have non-negligible effects on the galaxy that you're evolving. So actually, it's also important not to do just zoom simulations, but you need to consider statistics as well.
What are the level of differences in these images? Is it like 30% difference? Or?
I wouldn't be able to tell you that. Yeah.
Because I remember correctly, the stochasticity is already 30%, right? It just changes.
Yeah, but I think I show a bit later difference in the star formation, the stellar mass at a given time, and there is like a DAX difference in there. Yep.
I was wondering, those simulations only use CPU, but now they are GPUs, or is there something that prevents the use of GPU?
So good question. So these simulations are pretty much only, maybe not completely, but mostly CPUs. Let's see. Yeah. Chang'e, I think, it can be run on GPUs. I'm not sure whether it was at this point. But indeed, the future is kind of GPUs, and more codes are being rewritten to work on GPUs, and even new codes are being written for GPUs. So that's the future. Okay, so a bit more about subgrid recipes. From what I've shown, we resolve on the scale of the cell, of the width of the cell, or the mass of the SPH particles that you have. You resolve gravity and hydrodynamics. But in these large-scale simulation projects that I was showing you with kiloparsec resolution, you're far from resolving the chemistry of the gas, formation of stars. Individual stellar particles are 10 to the 4, 10 to the 7 solar masses. So these are stellar populations that you're forming. You don't resolve stellar feedback. You don't resolve the accretion, and feedback from black holes. So you use subgrid recipes to kind of mimic these effects in your simulations. So first of all, there is cooling. I think Katharina showed this plot in her talk. So you take this cooling curve, which is a composite of hydrogen and helium, and then this abundance of metals here. Here with, I think this is at solar metallicity, and you tabulate it. So you tabulate it according to the cooling rate, according to temperature and gas density, and actually to the redshift, because that affects the UV background, which also affects the cooling. And then you can quickly recover the cooling rate given the temperature and the density of the gas. If you want to compute all that on the fly, you have to compute different cooling rates for different species. Then, first of all, you need to include all those species in your simulations. Usually, you include one scalar, which represents metallicity. And you also have to compute just a lot of cooling rates, which are very expensive to calculate. So it's much cheaper to just tabulate it and calculate a table to calculate in each gas, cell, or volume element in your simulation. And kind of important also in a cosmological simulation, I think you usually don't include the formation of molecular hydrogen at all, and especially not the formation of molecular hydrogen at zero metallicity. So pretty much all cosmological simulations, they get around that by simply starting a cosmological simulation. The initial conditions, they have just a little bit of metals to allow the gas to cool below 10 to the 4 Kelvin. Then you need to form stars. So individual stellar populations are just modeled as collisionless particles. So you evolve them with just the pure, movement acceleration equation that I was showing you in the first slide. They have pretty high stellar masses, so these are stellar populations. Then when the gas becomes dense enough, you decide to form stars out of that gas. So you decide usually a density threshold above which you start to allow stars to be formed. And then you form stars at a rate corresponding to a star formation efficiency over a free-fall time times the density of the gas. The star formation efficiency is, there's a lot of ideas about what you should use for that. In the beginning, for most cosmological simulation, you use the cosmological average star formation efficiency, which is about 2%. This is a universal value, though. It's not really a local value. When gas collapses into molecular clouds, you actually find that in molecular clouds, star formation efficiency is much, much higher than that. So when you start to have higher and higher resolution in your simulation, you really want to diverge from that universal average, and you start to have locally high star formation efficiencies.
Is that an observational statement or an assumption that it's locally high?
That is an observational statement, yeah. So then there is a lot of variations in what people use in their cosmological simulations, everything from this cosmological average value to using 100% when it becomes dense enough. So you put a density threshold which is just very high for your simulation, and then you still constrain star formation from getting out of bounds. How am I doing for time, by the way?
We're still 40 minutes.
Okay, good. Question?
Formation rate, you say that there is threshold
Sorry?
You can form a star at wherever temperature?
So very simplified version is just the density threshold, but then people tend to add all sorts of constraints, including pressure, sometimes temperature, diverging gas. Gas has to be diverging. Trying to remember other things, but there are some additional constraints. Sorry? Molecular hydrogen, if you have that, if you include that in your simulations, yes, absolutely. Okay, and keep in mind, this actually totally affects the burstiness of the star formation that you're going to get, your choice of the star formation threshold, and also the local star formation efficiency that you have. If you put a small local efficiency, you're kind of artificially going to create a smooth star formation in your galaxy. Whereas, if you put a high local star formation efficiency, you have to kind of trust feedback, stellar feedback, to suppress the global star formation efficiency. And that typically gives you much more bursty star formations than you would have if you artificially suppress it like that. Sorry?
The dot is a time derivative, or is it?
It's a time derivative, yeah. So it's a rate of star formation in a given. Yeah, yeah. It's a rate of the star formation rate.
Sorry?
It's the rate of star formation.
The dot is a type of.
Ah, sorry. It's yeah. There shouldn't be a dot here actually because it's already yeah. Good point. So. As I alluded in the first slides, there is this general overcooling problem, which people realized pretty early on, that you need to have efficient feedback. Without it, you form too many stars. You also have too compact galaxies, and you don't get alphas from your galaxies. And they concluded supernova explosions are vital because I think there was the general acknowledgement that that's where you get most of the energy and momentum from your star formation. And also, it's actually important to enrich your galaxies with metals. So they tried to just do the simple thing. From each massive star, you get 10 to the 51 ergs of energy. So they tried to just dump those 10 to the 51 ergs from each star in your simulation into the local environment. And they found that it didn't do very much. So that's because of the more special overcooling problem. There are two ways to express that. So if you if you take your cell, which has a certain width, which is typically, say, a kiloparsec or something like that, and you dump 10 to the 51 ergs into that cell, then the temperature is actually going to scale as the width of the cell. Because the temperature is an energy per mass or per particle. So the larger the cell, the lower you're going to go in that cooling curve. So let's say you put your energy in a cell which is large enough that the temperature is in this region here, then you're at the top of the cooling curve and you're going to cool the gas very, very efficiently. Compared to if you had a smaller cell width and you had your temperature at higher values, then the cooling rate is actually much, much slower by an order of magnitude compared to if you have a larger cell. So this really affects the way that the cell can react to the energy that you put into it. So that's why in some subgrid recipes, people have used this stochastic supernova feedback, for example, in the Eagle simulations, where they just kind of store up the energy from individual supernova explosions to be enough to inject a temperature of 10 to the 7.5 Kelvin, which kind of coincides with the bottom of your cooling curve, where the cooling rates are the smallest. So this is just a way to get supernova feedback to be more efficient in your simulation, that if you did the stupid thing to just inject the energy of one supernova explosion in your cell. You can also express the special overcooling problem in terms of the Sadow-Taylor explosion. So a supernova explosion has several phases. So first there is a ballistic phase where you just have ejection of gas at tens of thousands of kilometers per second. That thermalizes and you get this adiabatic phase where you just have the pressure of the gas, which is pushing out. At the same time, the gas is cooling, and at some point, over a cooling time, you lose that pressure from the adiabatic phase, and you're left with a snowplow phase, where the gas is just moving according to the final momentum of the supernova explosion. So what you want to resolve is this adiabatic phase. If you put your supernova explosion into one cell, and your time step is long enough that you cool away all the energy before the gas has time to react, you basically get nothing from that explosion. So you really want to resolve that phase, and if you don't, you can instead apply the final momentum that you would get out of that adiabatic phase, which has been predicted from high-resolution simulations in the ISM of galaxies. So that's actually a method that people use very often in cosmological simulations. They put the final momentum that you get from a supernova explosion into the grid, into the surrounding cells from where you have the exploding star. There are also cruder ways to resolve that problem. One way is just to turn off cooling. So if you do that, you allow, for as long as you want, you allow adiabatic expansion to exist because there's no cooling in the gas. So actually this is also done quite often in cosmological simulation. It's called delayed cooling. And then you just have a time scale for the turn off of the cooling, and this makes for very efficient supernova feedback. Finally, as I was, I think, mentioning before, there is also a method where you just ignore the whole problem and decouple the supernova ejecta from the local gas. You can allow the gas to move even out of the ISM of the galaxy into the circumgalactic medium, so you kind of by hand you get very efficient galactic winds from your supernova feedback. Just to add to that, mostly in early cosmological simulations, there is also this interstellar medium equation of state, which is also a form of feedback. You don't allow the gas to cool below 10 to the 4 Kelvin, and anything above a certain density threshold, which is a function of the resolution that you have, basically, you just enforce this equation of state with increasing pressure with increasing density. So this kind of, people argue that this is kind of to replace unresolved turbulence and early feedback in your ISM. And this actually also artificially gives you very, very smooth star formation in your galaxies compared to allowing the gas to cool to low temperatures. Finally, there is AGN. So this is important, like I said, in massive galaxies, which is what we thought until the JWST. In reality, none of that stuff is resolved. This happens on tiny, tiny scales. What we can do is we can form sync particles at the centers of galaxies when they become massive enough. We have a seed mass, which is typically 10 to the 4 solar masses, something like that. And then we allow that to grow according to Bondi-Hoyle accretion, which is basically just sweeping up whatever gas it is crossing according to its movements. There is quite a bit of variations in the details of how you accrete onto these black holes or AGN or black hole particles, and also in how you do the AGN feedback. There is usually a radio mode and a quasar mode. But there are, the variations in this are kind of all over the place, and these are always kind of calibrated to get you the right suppression of star formation at high galaxy masses. Okay. And that's what I wanted to show when you, Christoph, were asking about the differences between the different recipes. So here is just again coming back to if you put all these variations in subgrid recipes for star formation and feedback. I don't think there is AGN in these simulations. You get these huge variations in how galaxies are forming their stars, even though they end up at more or less similar stellar masses, varying maybe by 30% or something like that, just because they were calibrated to hit these final stellar masses. But the way they get there can be very, very different. Okay, now let's see what happens if we try to have higher resolution than these hundreds of parsecs or even kiloparsecs that we had in these simulations 10 years ago. so now I take this from a nice paper by Vadim Semenov from this year, where he reran one of the TNG simulations with much higher resolution and allowing the gas to go to lower temperatures. So now you can already see that when you have higher resolution and you afford to have cooling in your simulation, you get a completely different ISM than you have in these classical cosmological simulations. Gas can actually start to fragment, form cold clumps, and you have a multi-phase ISM. So now people have been doing that also for the last 10, 15, 20 years. But as they increase the resolution and try to kind of minimize the assumptions that you make in these subgrid recipes, it actually turns out that it becomes harder and harder to suppress star formation and create galactic outflows that you see in observations. And it's not really completely clear how much the problem is still resolution and how much it is a lack of physics. So there are these two things that we think are wrong. I really think it's, to a large degree, still a lack of resolution. So in these simulations, you typically can resolve down to tens of parsecs in physical scales, maybe parsecs in some cases. These are still the sizes of molecular clouds in your simulations. And I think you really need to resolve individual molecular clouds to capture the early feedback from stars, the effects of stellar winds, the effects of radiation. But while we are still not able really to reach those kinds of resolutions in cosmological simulations, people have at the same time been exploring the effects of additional physics for feedback. Question?
Why would you say that resolution is good enough? That's always the question, right? Like, when is the resolution good enough to say it's like okay-ish?
So probably never. That's true, because you always have to add. There is always a new physical component that you need to describe with the subgrid model. That's true. But
what makes you optimistic about GNC scales and when you work on star formation at super high resolution within GNCs and you're probably not satisfied with their own resolution?
I didn't quite hear the end there. Sorry.
Okay, just the beginning. What makes you optimistic about GMC scale?
I'm optimistic in the sense that I think we can capture the effects of early feedback, radiation feedback, for example. I think we can capture the effects of probably these additional physics when we can resolve individual molecular clouds and the formation of stars in those clouds, and we can maybe tell better the relative effects of, for example, supernova feedback and those other models. We can tell how important these different feedback mechanisms are. That's my hope.
Sorry, can you clarify what is GNZ?
A giant molecular cloud, right? Giant molecular cloud. Okay, yeah. So anyway, people have been exploring those additional feedback mechanisms at the same time in relatively high resolution simulations, but keep in mind typically parsec or maybe even a bit more than that, 10 parsec. So now if you consider the energy coming from a stellar population from three feedback mechanisms, supernovae, stellar winds, and radiation, you actually find that most of the energy is coming from radiation by far. So 15 years ago or something like that, we started considering, maybe there is a strong effect from radiation feedback in galaxies. So many people, including myself, started developing radiative hydrodynamics in simulations and trying to include the effect of radiation and the transport of radiation in those simulations. And this turned out to have not very impressive effects on galaxy evolution in simulations. So there tends to be a little bit of suppression in star formation in low mass galaxies with radiation feedback. Not so much in massive galaxies. And it kind of actually suppresses alphas. So here's a nice cosmological simulation of a dwarf halo at high redshift from from Oscar Agams. And here you see the difference between just including supernova feedback and adding solar radiation to that. And mostly the difference is you get a little bit of suppression in star formation in this simulation here, which is the blue curve. Compared to the black curve for the case with supernova explosions only, but it is a kind of preventive feedback. It's not a ejecting gas as much as you have with supernovae, because you have burst your star formation with supernovae. Whereas if you add the radiation, you kind of heat the gas locally to about 10 to the 4 Kelvin. So you kind of make the star formation a bit smoother and less bursty. And that actually weakens the outflows in your simulation. So you kind of hold on to more gas, but eventually you form stars out of that gas that you hold on. So you just delay a bit the star formation, but eventually you get more or less the same mass of the galaxy. So you get effects from radiation feedback, but you don't get very huge effects from it. And certainly not enough to explain the strong suppression in observations. There have been a huge amount of MHD simulations as well, so you include magnetohydrodynamics in your simulations. But again, in cosmological simulations, in galaxy simulations, magnetic fields, they don't have a big effect on anything. There is a mild effect on the sizes of galaxies, but not very much more than that. However, MHD is also used for cosmic rays. So cosmic rays is a kind of a thing which has emerged over the last 10 years. Again, it turns out that there is a lot of cosmic ray energy which is ejected from supernova remnants, from shocks in supernova remnants. And the cosmic rays have the nice effect that they don't cool as efficiently as the gas. So they can inject much more momentum eventually to the gas without it cooling away. And when people include cosmic rays in their simulations, they tend to get much stronger outflows, like you see here, than the same kind of simulations where they exclude cosmic rays. So the cosmic rays are very helpful in generating galactic outflows by applying a kind of a gentle pressure gradient in the CGM and even in the ISM galaxies. And due to the same effects, basically, they can also reduce star formation. The problem with cosmic rays is that it's not very well constrained at all. How much energy you have in cosmic rays in galaxies, and also how quickly they diffuse in the gas in and around galaxies. So there is almost complete freedom in what you put into these energies and diffusion coefficients in your cosmic ray simulations, and depending on what values you use, you can create all sorts of effects.
I had a question about the image part because in my team there are other people working on jet and so on.
Mm-hmm.
And they somehow find that magnetic field is very, very important for
Yeah.
launching jets.
Yeah.
So is it not important because it's in subgrid models?
Yeah. Well, it's not a subgrid model, but it's just not resolved on the scales that jets become important, right? So in these large scales where the resolution is even a parsec or 10 parsecs, you don't care about magnetic fields. You care about them on smaller scales. And the same actually applies to radiation and I'm not sure about cosmic rays.
Can you explain qualitatively why the cosmic ray has the good taste of depositing its energy outside of the ISM but not completely away from the galaxy?
Why the cosmic rays deposit their energy away from the ISM?
They send it to infinity, right? They send it somewhere else in the galaxy, but
That's just an effect of the diffusion of the cosmic rays. So the cosmic rays at different energies, they scatter differently in the gas. So some, I don't even remember, I think higher energies, they kind of tend to diffuse faster, or the opposite, I don't even remember. Yeah, thank you.
diffusion coefficient, you can deposit it where you want. Is that your answer?
No. So typically, when people run cosmological so galaxy simulations with cosmic rays, you have one group of cosmic rays. So you put one diffusion coefficient. All the cosmic rays have the same diffusion coefficient, and you inject them where you inject the supernovae, and then you just allow them to diffuse according to whatever diffusion coefficient you put in by hand into your simulation. So you are kind of propagating them actually with very similar methods as you use for radiative transfer. So you're allowing them to propagate. You're not injecting them selectively, anything like that. Just checking the time. So I guess I have about 20 minutes, something like that. Yeah. So let's speed up. So I want to say a few words about reionization simulations, mostly because I've been working quite a lot on that. So now, I mean, these are cosmological simulations, so they fall formally into the topic of the lecture here. Reionization simulations, they tend to fall into two classes. Pratika, she was more describing large-scale reionization simulations, where you kind of try to explore the topologies of reionization regions, reionization bubbles, how they grow, how they merge with each other, and you make predictions for the SKA, basically. For 21 centimeter emission. There are also reionization simulations where we try to resolve the sources of reionization. So which galaxies are responsible for producing the photons that reionize the intergalactic medium, how that radiation can escape from those galaxies. And in those simulations, you kind of tend to, you minimize the size of your volume because you want to resolve the sources, right? Whereas in the large volumes, you cannot resolve galaxies. So I'm really interested in the latter kind of simulation. So we use the Sphinx simulations, which are shown here, to kind of try to resolve what's going on inside the galaxies and how the alignment continuum photons are produced and how they escape from those galaxies into the IGN. So here's just to show one of the Sphinx simulations. So we run here a 20 megaparsec box, where we include radiative transfer on the fly, so radiation hydrodynamics. We form these cosmological structures, so filaments and halos, which gas falls into, forms galaxies. The galaxies, they emit radiation, some of which escapes from the galaxies and can reionize the intergalactic medium, heats it up like Pratika was showing. You get these reionization bubbles, which are heated to 10 to the 4 Kelvin. And then inside those, you have galactic wind bubbles, which are more like 10 to the 6 Kelvin. And then as a result of that, you slowly reionize the volume. It's also just to give you an idea of the effort which is included in running cosmological simulation. You need to have access to tens of thousands of cores, of CPUs in this case. And it can take quite a long time, actually, to run a simulation. It took 2 years to run this simulation. Here, I want to focus in on one of the environments in the Sphinx simulation. So just to show you how the radiation is produced and escapes from those galaxies. So what you see here is in pink. There is the gas. And you see these kind of flashes of yellow or red, which are creating these ionization bubbles, and the gas is becoming ionized. So what's going on in these simulations and in many other simulations, similar simulations where you kind of try to resolve what's going on inside galaxies during reionization, is this kind of breathing. I think it's described as breathing of galaxies, where you have this cycle where gas falls into the ISM of galaxies. You have high densities and intense star formation as a result of that. But after just a few million years, you start to have supernova explosions. The supernova explosions, they clear away the gas, and all of a sudden, the alignment continuum radiation, which is being produced, it can escape away from the ISM because of that supernova clearing. But that also shuts down star formation. So after a few million years more, the galaxy becomes dim, and you have to wait for, say, 100 million years for the gas to kind of start coming back into the galaxy, and the whole cycle repeats itself. So this is very typically seen in reionization simulations, provided that you have this bursty mode of star formation. So we try to use that to predict escape fractions from the simulated galaxies. So we have made our prediction here, where there's kind of a pretty strong scaling of galaxy mass. So the low mass galaxies, they have relatively higher escape fractions than high mass galaxies, and that's because of the relative strength of supernova feedback and disrupting the interstellar medium in low mass galaxies. Whereas in massive galaxies, they don't do a lot of damage, and you have low escape fractions at all times. However, there are many, many simulation projects, and the results are actually all over the place. So it's really, it's a bit chaotic nowadays, I think, in predicting escape fractions from cosmological simulations, because there is no agreement at all. I think many tend to find that there is a kind of a scaling with mass, that low mass galaxies do tend to have the highest escape fractions, so there is kind of consensus on that. But the exact place where it peaks, for example, that actually depends on the strength of your feedback on your subgrid recipes. So I think there is kind of maybe a qualitative agreement on that, but quantitatively not so much. And the magnitudes also are all over the place. And just to hammer that a bit more, I think the problem is, again, things are not resolved at all. If we run now idealized simulations of individual molecular clouds where the resolution is a subparsec, you have basically 100% escape fraction of your radiation from the stars that are forming. So you see here radiation kind of being emitted from individual stars. In the beginning, it doesn't escape very much. You can see that in this plot here. So this is the instantaneous escape fraction, but after a few million years, a couple of million years after you formed the massive stars, the radiation has actually, by itself, carved holes into the molecular clouds way before the onset of supernova explosions. And the radiation is escaping from the cloud. It doesn't say whether or not the radiation is escaping from the interstellar medium, because we don't include that in those simulations. But on the scale of molecular clouds, it's not really the same thing happening as in the cosmological simulations, where the escape fractions are powered by supernova feedback. Here, the escape is powered by the radiation itself. Also, just to mention reionization feedback, because it was being mentioned yesterday, the day before yesterday. So that absolutely happens in reionization simulations, not just in Sphinx. I'm showing Sphinx here, but it also happens in other cosmological simulations, for example, in the Cosmic Dawn project. Here you see qualitatively the effect of reionization on the cosmic web. So this is a simulation where we just turn off the radiation from stars. And here you see the effect of the radiation ionizing the universe and kind of diffusing the filaments, the gas filaments in the cosmological web. And as a result, you have a strong suppression of baryons in low mass halos as a function of redshift. So at very high redshift, there is little suppression in the baryons in low mass halos. But as you progress towards the redshift of reionization, you get a very strong suppression in the least massive halos. And again, simulations, they completely agree on this effect, but there is a bit of variation in at what masses this becomes important. The first stars, Andrea did such a good job on this the other day that I'm not going to say very much. Except, well, the big question in terms of reionization, at least, is the IMF, because that tells you how much feedback is coming from those stars, how much radiation is coming from those stars. So what contribution would they make towards reionization? So if you want to resolve that, there's no way you can do that in a cosmological simulation, not yet at least. So you have to run these idealized simulations to kind of try to predict the IMF of a collapsing molecular cloud of gas into population 3 stars. And you need to include a lot of physics. There is the effect of magnetic field, magnetic braking. There is the effect of radiation across different wavelengths on the formation of, on the fragmentation and the formation of the stars. People have started to include more and more physics in those kinds of idealized simulations, but again, there is very, very little agreement on the IMF that you get from those simulations. It tends to become more top-heavy with radiation feedback. There is not very much exploration on magnetic fields yet. And also the problem with magnetic fields is we don't even know whether there is a magnetic field during the formation of POP3 stars. So the problem is quite difficult. It's not even just a question of including the physics. It's just knowing what's going on at these extreme redshifts. We have used cosmological simulations to try to predict at which times and in what kinds of halos the first population 3 stars are forming. There is kind of agreement that they form between redshifts, I think 20 and 30, something like that, maybe a bit higher. And there is also kind of agreement that they form in halos which have about a bit less than 10 to the 6 solar masses, 10 to the 5 to 10 to the 6 solar masses. So this is just doing simulations where you include the chemistry necessary to form molecular hydrogen from no metals, from deuterium. But you don't track the final collapse of the clouds. You track until the clouds is unstable, and then you stop your simulation and you just find where these clouds form. There have also been predictions from kind of reionization, cosmological reionization simulations to try to tell where we would expect the last population 3 stars to form. And people tend to find that this is at the epoch of reionization, towards the end of reionization, and even a bit lower redshifts than that, although they find here that they stop forming at redshift 5. So this is from the thickened zoom simulations. This is a cosmological zoom simulation of an environment around a galaxy cluster. And they find that you have like pristine gas star formation happening in these satellite galaxies down to redshift of about 5. And then at this redshift, you kind of shut down star formation in these low mass halos due to the starvation from reionization feedback. So after that time, you don't have any pristine halos at low mass which are forming stars anymore. 15? Yeah. It's going to be tough. High redshift galaxy simulations. So now coming back to 10 years ago, with these large-scale simulation projects, they were doing exceptionally well at low redshift and producing the stellar mass function, Koenig-Schmidt, etc. But if they looked at high redshifts with the observations that we had, they weren't doing so well. People already knew that. There was already a problem at high redshift with suppressing star formation. And then there was the JWST a few years ago, and we started seeing these bright, massive galaxies at high redshift, which made the problem even worse. There was this nice paper early on which just looked at how just assuming that you form stars out of all the gas available in the most massive halos in the universe, how massive galaxies would you expect to find? And according to these early observations, you were actually forming galaxies that were more massive than would theoretically be possible at all. So now, all of a sudden, numerical people, they had been trying to suppress star formation, and now all of a sudden we have to kind of try to boost. We have to explain how there is this boosted star formation, which is very converse to our nature for the last 20 years. However, most of these detections are actually turned out to be not at this extremely high redshift. They turn out to be lower redshift. I think it's called interlopers. So the problem was not really as bad as it seemed here. Still, there was a kind of a flurry of papers from usually people who have been doing a lot of work on alternative cosmologies, modified gravity and stuff like that, making very dramatic statements that lambda CDM is dead, showing here a comparison to these early galaxy cosmological simulation projects and how we were seeing galaxies which were orders of magnitudes more massive than anything you could get from those simulations at high redshifts. This has turned out to be, wrong. But there are, if you look at the literature, there are still papers coming out that are citing works like that, saying lambda CDM is dead, so we need to consider other options. But really take that with a grain of salt. There were also other works who were comparing spectroscopically confirmed masses and redshifts to existing simulations, some of which are kind of targeted towards high redshifts, the obelisk simulations, for example, and finding that if you now compare to the observed galaxies in 22, you could, in at least some of these cosmological simulations, you could reproduce the same kinds of galaxy masses as we were finding in observations. So maybe not a huge problem. Okay. Just to show the same thing, I think I'll skip over that. It's again showing we can largely reproduce what was observed in 22 with these simulations. Again, from the Renaissance, very high resolution, high redshift reionization simulations, doing a bit of extrapolation because the simulation stopped at pretty high redshift because they were so high resolution, but extrapolating from that, they could kind of reproduce the ballpark of galaxy masses that were seen in observations, concluding there is no tension with observations. But then we actually started getting more and more of those massive galaxies, so it seemed to enhance the problem a bit. Here, just observations from Yuichi Harikane, finding that some of these objects turned out to be at lower redshifts, but I think there was, somebody mentioned an 80% confirmation of the objects which had been photometrically observed. So it seems that the problem was getting a bit of a problem. Still, last year, if we compared two theoretical models, the luminosity function could still kind of be reproduced by fairly simple analytical model, assuming constant stop-motion efficiency over redshift. But if you now go to the next paper by Yuichi, showing even more bright galaxies at high redshift. So you're going to 63 from 25 the year before at redshift above 8. Now it starts to become a problem. There are clearly way too many bright galaxies at high redshift. There is still, it's not very large statistics, and the error bars are quite large, but it starts to be a very visible excess. And there is also the problem that it seems to be too much stop motion at high redshift compared to what people can reproduce with analytic model and with simulations. In addition, there are these problems that we tend to observe disky galaxies, but we do observe disky galaxies at extremely high redshifts, redshift 5, 6. There are strong hints of strong AGN activity at these high redshifts, and even quenched galaxies around cosmic noon. There have been many models to individually explain these things. There have been many alternatives to lambda CDM, which are still ongoing. There is the feedback-free model by Avishai Dekel, where the gas is just so dense and pressurized at these high redshift that feedback just becomes puny and has no effect. There is the attenuation-free model, so ask Andrea about that, where gas is kind of just ejected due to strong feedback in these early galaxies, if I understand correctly. Top-heavy IMF is completely a possibility, giving you bright galaxies at lower masses. And bursty stop motion can also help. So, these are pretty much all plausible. Many of them are plausible, and probably a combination of these models is a solution to this bright galaxies at high redshift. And we need dedicated high redshift simulations to try to probe these scenarios and see if they work. There are already efforts to do that. The nice thing now, actually, about JWST is that we are looking at galaxies at very high redshift. In the past, if you wanted to compare to redshift 0 observations, you had to run your simulation for 14 gigayears. If you want to compare to redshift 5 observations, you basically have to run for 1 gigayear. So that's at least an order of magnitude cheaper than running a simulation that goes to redshift 0. And actually, it's much more than an order of magnitude cheaper because of other effects in those simulations. So high redshift is actually, in a way, very nice. So you can afford to go to higher resolution. Like Vadim Semenov did in this work here, where he takes a galaxy initial conditions from the TNG and applies much higher resolution and kind of improved subgrid models that adapt to the higher resolution that he can afford in those simulations, forming a multi-phase ISM. And as a result, the galaxy that he simulates looks completely different to its equivalent galaxy, starting from the same initial conditions in the TNG simulation, which is kind of natural. You kind of would expect that if you can have a much higher resolution in your simulation. He gets much burstier star formation, and he gets disky galaxy compared to the TNG one. So you kind of he can reproduce this particular effect of disky galaxies at cosmic noon. However, you can already see a hint here that the galaxy is also a bit more massive than the TNG galaxy, and actually now the problem is these galaxies we can kind of reproduce observations, at least some of them at high redshift, but we cannot afford to run these simulations down to redshift 0. So now we have the kind of opposite problem to what we had before. We can reproduce something at high redshift, but we don't really know how it does at low redshift, and we kind of need to do both, right? And also, actually, in this work, there is a kind of a boosted feedback as well. He uses 5 times the number of supernova explosions that you would expect from a Krupa IMF. You could apply, maybe there's a more top-heavy IMF, but really we don't know what that could compensate for. Is it still a lack of resolution, or is it a lack of physics in the simulation? Bursty star formation can also help a bit. It's been shown in some works here in the fire simulations that if you compare a bursty star formation in your simulation to a smooth one, you can boost a bit the UV luminosity function. Thank you. But there is not really agreement on that. I think that also depends a bit on the subgrid recipes that you use, whether bursty star formation helps or not. Maybe I'm going to fast forward a bit. There is a nice, the firebox simulation is kind of the same models that they use in the fire zoom simulations. And doing that in a cosmological volume, they actually can reproduce largely the UV luminosity function over this range of very high redshifts. Although there is really a lack of statistics here at the extreme redshift end. But again, and they can reproduce also pretty much this star formation rate density as a function of redshift. But again, there is the same problem that here they actually do go to low redshift, and they do find that they actually fail at low redshift. So they do pretty good at the high redshift end. But using that model, it forms too many stars at low redshift compared to observations. I think I'll just skip over this. There is a kind of a skeleton in the closet here, for example, when you're seeing the UV luminosity functions compared to observations, which here is a pretty good comparison. I think we should be comparing the blue here to the shaded region. But there is a completely phenomenological model for dust absorption in those simulations. So they are kind of just adjusting the dust content to match the observations, as I read it. And that's because there isn't in most of these simulations there isn't a model for dust formation and destruction. So we just kind of apply that in post-processing, and usually we kind of maybe subconsciously make that fit the observations a bit better. there have been some attempts to include the formation of dust and destruction of dust in simulations. So here with the species dust model. But finding that it's actually quite hard to grow dust at high redshift here in the simulation compared to what's found in observations at high redshift. So there are estimates at high redshift for the dust contents of galaxies, and it's much more than can actually be produced with the dust models that we think are correct and work well at low redshift. Maybe I'll include this. So there's been these observations of AGN that are almost the same mass as the host galaxies at high redshifts, and therefore there have been attempts to look at in simulations. Can we reproduce these black hole masses in simulations? There are more and more efforts on this. I'm highlighting one from a few years ago. And it's really hard. It's almost impossible to grow AGN in high redshift simulations of low mass galaxies, actually at any redshift. It's more a function of the mass of the galaxy. So here, from Maxime Trebic, if you don't include any feedback in your simulation, then you can grow an AGN, no problem. There is gas coming to the center of the galaxy. It can accrete onto the black hole. The black hole can grow. But when you start to include any feedback in your simulation from the AGN or from the supernovae, they tend to clear away the gas in these low-mass galaxies, and the AGN has nothing to feed on anymore, so it doesn't grow. It has to reach the mass where supernova feedback starts to become inefficient, and then the black hole can start growing. I think I kind of ran out of time now. Yeah. So we can talk about mock observations over coffee. They're very interesting. Thank you. Using different speeds of light.
Yeah.
You're doing reionization, right?
Yeah. What prevents people from using the exact speed of that, apart from computational?
So I had a slide in the very beginning showing the Courant condition. So usually when we do radiator transfer in simulations, we use a moment method. We don't, instead of, the naive thing to do is to trace rays from sources to destinations, but it's very expensive because you need a lot of rays and it's just expensive. So we use a moment method where we kind of direct radiation between cells or particles. And then you're subject to the Courant condition, again, which says nothing should flow across more than one cell width in one time step. So that gives you a time step which is very, very small because it scales as the inverse of the speed of light. Whereas normally for hydrodynamics, it's the speed of the gas, right? So your time step becomes 1,000 times smaller than in your hydro simulation. So you have to do 1,000 times more time steps. So that's why if you put a full speed of light, it becomes very, very expensive to run your radiation hydrodynamical simulation. And the very, very crude way of cutting down that cost, you just reduce the speed of light by a factor of 1,000, and then you're back to the hydrodynamical time step size.
I have a very naive question. You have extremely high resolution up to redshift about 14, 15. Is it possible to take this as a starting point for new simulation that is much lower resolution to get to the lower redshift?
Yeah, so, and people are already doing that to a degree. I don't remember which project or projects are doing that, but they do. To try to probe how would that simulation, if it works at high redshift, how would it do at low redshift? So that's one way to go, but how predictive it is, I don't know.
Okay, other questions? Yes, please.
I have a question on the gravity, let's say. In this kind of simulation where we have a large box length, let's say, of 10 to 9 megapascals, so we use
Sorry to say that last word again.
we use Newtonian gravity, no?
Yeah.
But we know that gravity not act instantaneously.
Ah.
If we have why we move particles of
That's a tough one. I think, as far as I remember, unless something like the gravity is predictive in a way. So if the particle is moving in a trajectory, there is no effect from the large distances across which it takes time for the gravity signal to move. It's only if it like changes suddenly direction, then it becomes an effect, as far as I know. I don't think that makes a difference in large-scale cosmological simulations, because everything is it's only on small scales that sudden things happen like that, right? So I think for the large-scale, cosmic web, that's not an issue. Like, if the sun were to disappear, now we only know about it in 8 minutes. Yeah.
Or the effect becomes important when you're on the scale of the horizon, right? So if they're much smaller than the horizon, then it's an approximation.
Yeah.
Questions? No other curiosity or anything? Anything was clear? Okay, then we are perfect timing. Thank you, Joakim, again.
Thank you.
We reconvene in 30 minutes, so at 10:30.
Thank you.